We are in section 6.2 volumes. Under appropriate conditions, the same strategy used in the previous section can be used to find the volume of a solid. The idea is to divide the solid into slabs, approximate the volume of each slab, and then add the approximations to form a Riemann sum, and take the limit of the Riemann sums to produce the integral for the volume. So let S be a solid that extends along the x-axis and is bounded by the left and the right, respectively, by those planes that are perpendicular to the x-axis. And you can see in the picture down below at A and at B. Find the volume V of the solid, assuming that its cross-section area AX is known at each of the intervals. So pretty much it's like if you had a cake and you were to cut it into pieces, and think of a rectangular cake like in the picture, and you can find the area of each of those slices of cake. You can cut out a small cross-section area or a piece of cake, and you can calculate the area of that, and then by adding up all those little areas that we would have, you can get that total volume of that cake. So to solve this problem, we divide the interval A to B into n subintervals, thereby dividing the solid into n slabs. If we assume that the width of the kth subinterval is delta x, then the volume of the kth slab can be approximated by the volume of that, which would be the area times that width, which is going to give us the volume. And it says of the right cylinder of width with a height of delta x sub k and a cross-sectional area that we're going to call A of k xk star, where xk star is the point in the kth subinterval. So in the pictures, you can see the cross-section in the area that it would have, and this area right here is just our delta x sub I. So adding these approximations yields the following Riemann sum. So again, you'd have your area times that width, which would give you the volume. And then taking the limit as n increases, the width of the subintervals approaches 0 yields in the definite integral. And so we get the following. So it says, let S be a solid bounded by two parallel planes perpendicular to the x-axis, or at x equals A and x equals B. If for each x in AB, the cross-sectional area of S perpendicular to the x-axis is A of x, then the volume of the solid is going to be, and again, we have the volume, which we're going to be integrating from A to B, and it's that area times that width. And again, this is for the whole part in between the values of A and B. So a solid of revolution is a solid that is generated by revolving a plane region about a line that lies in the same plane as the region. The line is called the axis of revolution. Many familiar solids are of this type. And so you can see in the diagram below, there's the axis of revolution. And so 4 axes of revolution. And for us, a lot of times it's just going to be y equals 0. Not always. We could be revolving around maybe y equals 2 or even x values like x equals 7. But you're going to go ahead and take that area that you would have, and you're going to rotate it around your axis of revolution. And when you do that, it's going to create a new shape now that is going to be able to find the volume of it. So it says, let f be continuous and non-negative on the interval from A to B, and let R be the region that is bounded above by y equals f of x, and below by the x-axis, or y is equal to 0. And it says, and on the sides of the lines by A and B, find the volume of the solid of revolution that is generated by revolving the region R about the x-axis. So if you see here, we're going to take this area that we have, this region R, and as we spin it around the x-axis or around y equals 0, as you do that, you're going to create this. It looks almost like a flower, like a tulip or a drum. And you'll notice that if you were to cut part of it, it's going to make circles. They look like what we're going to call discs. So to find the area of a circle or of a disc, we have pi r squared. And so for this problem, our radius, or our r here, is equal to our function f of x. And so that changes. It's not a constant value like we saw in earlier math courses where maybe the radius was 2. If you look at this, as you go towards the left of that shape, that radius gets smaller, and as you go towards the right of that function of that shape, it's going to get larger. So it's changing, so it's a function. And so our area is going to be defined as pi times that function, which is f of x, which would be the same thing as our radius, so we would have to square it. We can solve this problem by slicing. The cross sections of the solid is a circular disc of radius f of x, so this is equal to our r, our radius, and the area of this region is going to be pi r squared, or pi f of x squared. So to find the volume of a solid with a cross section of a circular disc, we're going to have our volume is equal to, and we are going to be integrating again from a to b. And then we have pi r squared, and so again pi times our function, which is our radius since it changes, squared, and then dx since we are integrating with respect to x. And another way to see this too, if you were to take one little slice out of this, our approximating rectangle like we did in the last section, and rotate it around, as you rotate that around, it will make a disc, or a circular disc, a circular region. And so we can use that to find the area. And again, that radius is going to be the height depending on that function f of x. So right below this we have an example. The example says find the volume of the solid that is attained by rotating the region bounded by the given curves about the specific line. Sketch the region, the solid, and the disc. And so for this one we have y equals 1 minus x squared, y equals 0, and it does tell us that we're rotating it about the x-axis. So first thing we need to do is sketch this. And I notice that we have y equals 1 minus x squared, and we also have the value of y equals 0. And so y equals 0 is along that horizontal axis, the x-axis. And then graphing y equals 1 minus x squared. This is half of a circle, a semicircle. And so going ahead and substituting in 0, you get a value of 1. That radius of 1 going out to the left to negative 1 at 0 and to 1. So it's our semicircle, or half of a circle. And so now what we're going to do is we're going to rotate this about the x-axis. And so we're going to rotate this way. So if you can imagine half of the circle, this is the shape, this region is going to get rotated around, and as you rotate it around it becomes into a sphere. And so if you think about having a approximating rectangular region, which we'll go ahead and draw here, which also that width would be a delta x. But as it's rotating around, if you think about that one little piece, if you rotate it around the x-axis, it's going to make a disc. It's going to make that circular region. And so it does say to sketch the region, the solid, which we need to also sketch. So as we rotate this whole entire region, we're going to end up with a circle or a sphere. And that disk that we would get, and again, do the best you can with drawing. And so our radius for this function, for this disk, is defined by the function that we have. So our radius is defined by the function that we have, and for that it's going to be the top function minus the bottom function, which for us the bottom function is just 0. And so we're going to have our, but I'll write it down because some of them do get a little bit more complex, 1 minus x squared minus 0, which is just going to be 1 minus x squared. And so our radius is going to be 1 minus x squared. And that width that we would have would be our delta x. So our area is going to be pi r squared, which for this problem, our radius is going to be 1 minus x squared, and then we're going to square that. And so if you were to multiply this out and combine your like terms, you're going to have pi times 1 minus 2x squared plus x to the 4th. And so to find our volume, which is what it would like us to do for this problem, we are going to be integrating from a to b of our area times dx. We calculated our area down below, and I'm going to go ahead and put the pi out in front of my integral since it's just a constant. We are integrating from -1 to 1. And then we have 1 minus 2x squared plus x to the 4th dx. And so integrating this, we have pi x minus 2/3 x cubed plus 1/5 x to the 5th. Evaluating from this from x equals -1 to 1. And you can use some symmetrical ideas to simplify our integral, but I will just go ahead and leave it as this. And substituting in 1, we have 1 minus 2/3 plus 1/5 minus pi, and then substituting in -1, we get -1, and then we're going to have plus 2/3 minus 1/5. And so this is going to work out to being 2 times pi, which is 1 minus 2/3 plus 1/5, which again you could have used that idea of symmetry, noticing that the left and the right side of the y-axis are identical, or by just factoring out a negative from the second parenthesis, you'll be able to arrive at the 2 since they're going to match exactly. 2 pi times 1 minus 2/3 plus 1/5. And then working this out, we arrive at 16 pi over 15. And so this is our volume. We have another example on the next page that we're going to go ahead and circle and work on this one together in class. Let f and g be continuous and non-negative on the interval from a to b, and let R be the region that is bounded above by y equals f of x and below by y equals g of x. And you can see that in the picture right below. And on the sides by the line, x equals a and x equals b. The volume of the solid of revolution that is generated by revolving the region R about the x-axis can be found by slicing the cross-section of the solid taken perpendicular to the x-axis at the point x is a washer shape. So it's circular, it's like a disc, but it has the middle missing out of it. And so we call this, it's washer shaped. It's a washer. And it has an inner radius from g of x and an outer radius of f of x. So in order to calculate the area of the washer, we're going to have to do that outer circle minus the inner circle, and that's how we would find that area. So for a washer, so which is similar to a disk, however it has that inner circle missing. Our area is going to be pi r squared minus pi r squared, meaning pi r squared for the outer circle that we have and pi r squared for the inner. So for this, we are not dealing with nice numbers for our radius. Usually we don't deal with a radius of 4 that is a constant value. We are dealing with a function that's changing depending on where you are on that graph. And so the outer function would be f of x, and that inner function would be g of x as you rotate it around our x-axis. And so the area is going to be pi r squared, so pi f of x squared minus pi r squared for the inner, which is going to be pi g of x squared. Or you can factor out the pi and just have f of x squared minus g of x squared. And so this box right next to that says the volume of a solid with a cross section that is washer shaped is going to be v equals pi times the integral from a to b of f of x squared minus g of x squared dx. Again, we are rotating this around an x-axis, and the width would be that delta x. So right below this we have an example. This example says find the volume of the solid that is obtained by rotating the region bounded by the given curves about the specific line. Sketch the region, the solid, in a typical disk or washer. So part A has f of x equals 1/2 plus x squared, g of x equals x over the interval from 0 to 2. And we're going to revolve this about the x-axis. So again, the first thing we're going to do is go ahead and sketch this. I do have my graphs, and I do know that we are between 0 and 2, so I do not need to find an area enclosed by anything. So it does want us to sketch the region, and then the solid, and then also the typical disk or washer. So first thing that we're going to do, sketching this, we're going from 0 to 2. And the first graph that we have is a parabola. And at 0 we would have 1/2, and at 2 we would end up with 4.5. So I'm going to go up to 5. So we're going to start at 1/2 here, and then we get 1.5, and then we get 4.5. And so sketching this on, and this is my graph y equals 1/2 plus x squared. The second graph that we have, g of x, is just y equals x, a straight line. So 0, 0, 1, 1, and then 2, 2. And so we have our region. I'm going to go ahead and draw lines here for the values from 0 to 2. And the region that we have, I'll go ahead and shade. And so now what we're going to do is we're going to rotate this region about our x-axis. So if you can imagine taking this little strip that we have here, this little area, and rotating it around, it will be reflected, and I'll go ahead and draw this down right below. But you can also think about, I'm going to draw one rectangle on here. So approximating rectangle, and you kind of think about that one rectangle being also rotated around. So that was the region that we just drew. Next we're going to draw the solid, and so the solid is going to be what we would rotate around. And so again, we're going out from 0 to 2, and as we rotate this around, what's going to happen? So I'm going to go ahead and sketch it again. And when this gets rotated around, this little rectangle that we had originally drawn, as it rotates around, and this whole entire region rotates around, it's going to make a shape almost like a horn. And this little rectangle would be rotated all the way around down here. And again, it's going to make, so it'll be an inner circle and an outer circle that we would have. And this outer circle is going to make a washer. So this is a washer. And so in order to find our area here for this, we would have to do pi times the outer radius and then square it, minus pi times the inner radius and square that. So that's going to be for our area. And then to find our volume, we're going to multiply that by our delta x or our dx as we integrate. So volume is going to be, and the formula is right at the bottom of the previous page. So I'm going to start off with pi, and then we're going to be integrating from a to b, and since we're integrating with respect to x, since we have a delta x on here, we're going to go ahead and put those values of that we would be integrating from our x values, which goes from 0 to 2. And so that outside radius is going to be 1/2 plus x squared, and then we square that, minus the radius that we have from the inside function, and the radius that we have from the inside function is y equals x. And so we're going to take our radius, which is x, and square that. And then we need to also include the dx, since that would be the width in order to give us that volume. So area times the width would give us that volume. Make it three-dimensional. And from this, we get pi times the integral from 0 to 2. And we have 1/2 plus x squared squared, which is going to work out to being 1/4 plus x squared plus x to the 4th minus x squared, and then dx. And then we have pi times the integral from 0 to 2. And combining our like terms, we end up with just 1/4 plus x to the 4th dx. And so integrating this, we have a pi out in front, and then we have 1/4 x plus 1/5 x to the 5th, evaluated from x equals 0 to 2. And then going ahead and substituting in 2 first, we have 1/4 times 2 plus 1/5 times 2 to the 5th minus pi times, and then substituting in 0, we just get 0. And so working this out, we're going to end up with pi times 1/2 plus 32 over 5. Getting a common denominator, combining those, we're going to end up with 69 over 10 pi. We have another example right below this, which is B, which I'm going to go ahead and circle, and we will work on that one together in class. And on the next page, we have another example, which is C. We're going to go ahead and do that one right now. We're given y equals x to the 3rd, y equals 1, x equals 2, and we're rotating it about y equals -3 this time. So first thing we're going to do is go ahead and sketch that region. And the first equation that we have is y is equal to x cubed. So I'm going to go ahead and sketch that, and then I'll put in the y is equal to 1 and the x is equal to 2, and hopefully I can see the region at that point. And then we can rotate it. So first thing that we're going to do is if we graph x to the 3rd, I notice 0 cubed is 0, 1 cubed is 1, 2 cubed would be 8. So I'm going to go all the way up to 8. And then going out to 2. So I have 0, 1, 1, 0, 0, 1, 1, and then 2, 8. And if I were to keep going with this, I'd have 3 to the third and so forth. But I do realize that I have a value, an equation here, x equals 2. And so graphing that line. And then we also have an equation of y is equal to 1. And so the region that's enclosed by all 3 of these graphs, I'll go ahead and shade. It's almost like a triangle. And so this time we're not just rotating around the x-axis, we're actually rotating this around y equals -3, which would be right here. So y equals -3. So I'm going to go ahead and draw a dashed line here so I can show that it's being rotated around. And so if I were to make a rectangle here, or approximating rectangle, and so that first value that we have there, which is at 1, 1, is going to reflect over that line by 1, 2, 3, 4 places. So for the second point, it would be the 4 spaces away, just like that first point that we had, and then a total of 8 more. So and again, sketching it the best that you can. Go ahead and draw my region here. And so as I rotate this around the line y equals -3, we have like almost like a horn looking idea. And that rectangle is also going to rotate. So as this rotates around, you're going to have an inner circle and an outer circle. So we're definitely dealing with a washer here. So there's my washer. And so now we need to discuss the inner and the outer radius, since it's a little bit more challenging as you rotate around something that's not the x-axis, because with the x-axis, the equation that you're rotating around is y is equal to 0. And so with this, we have our inner radius and an outer radius. So for our inner, let's look at that first. I'm going to go ahead and call that r is equal to, and that inner radius is going to be the distance from the base of our rectangle down to the line y equals -3. And with this, and again, we always do the top minus the bottom, and so with this, it's constant. That whole entire inner radius never changes, since we're dealing with a horizontal line as we rotate that around. And so our inner radius would be 1, which is our value that we have that we're dealing with, minus the value that we're going around, that we're rotating around, which is -3, which works out to being 4. So our inner radius is 4, which you can literally count on your graph. You can count that that's 4 spaces there. And then we also have our outer radius, which is dealing with a function now that changes. That's in terms of our values of x. And so as this changes, you can see as it goes to the left, that outer radius gets a lot smaller, and going to the right of our graph, the outer radius does get definitely larger. And so dealing with our radius here, it's going to be that outside part of it minus the inside part of it. And so the outside part that we have that we're rotating around is going to be defined by x to the third. and it's adjusted around that line that we are rotating about, which is -3. So we need to do minus -3. And so our outer radius is going to work out to be an x cubed plus 3. So now when talking about our area, we're going to have pi times the outer radius squared, which is going to be x cubed plus 3 squared, minus pi times our inner radius squared, which is just 4. And again, we can factor out that pi and simplify it from here. So in order to find our volume, we're going to have pi times the integral from, and we are integrating, our x values are changing from 1 to 2, times the outer radius squared, which is going to be x cubed plus 3 squared minus the inner radius squared. And again, since we are dealing with a delta x, which is our width, I'm going to go ahead and put dx, and we're integrating with respect to x also, and those values that we have, our lower and upper limits of integration, are in terms of x. From here, we can multiply out x cubed plus 3 times x cubed plus 3, and when we do, we simplify that, we end up with x to the 6 plus 6x cubed plus 9, and then we have minus 4 squared, which is 16, and then dx. And then continuing to simplify this, combining our like terms, we're going to end up with x to the 6 plus 6x cubed, and then 9 minus 16 is going to become -7, and then dx. And from integrating this, we have pi out in front, and then we have 1/7 x to the 7th plus 6 over 4 x to the 4th minus 7x. And we're going to evaluate this from x equals 1 to 2. So evaluating it 2 first, we have pi times 1/7 times 2 to the 7th plus 6 over 4, which simplifies to 3 over 2, 2 to the 4th minus 7 times 2, minus, and then substituting in that lower limit, which is just 1, we have pi times 1/7 plus 3 over 2 minus 7. And simplifying all of this and order of operations, we end up with 471 over 14 pi. So the methods of discs and washers also work for regions that are revolved around the y-axis. And so it says the limits of integration would be the minimum and the maximum y values, and the integration would be performed with respect to y. So we'd be able to do the same thing. And again, this is an example of a disk. And this is also an example of a washer. So again, the same idea, but instead of rotating it around y equals, like this example that we just did, y equals -3, we would now be rotating around x equals -3. And then for a disk, we would be rotating that around the y-axis instead of around the x. So on the next page, it says, let S be a solid bounded by 2 parallel planes perpendicular to the y-axis and at y equals c and y equals d. If for each y in CD, the cross-sectional area is of S perpendicular to the y-axis is AY, so our volume would be the integral from C to D of the area with respect to y times dy, since we would be integrating this with respect to y, and that width would be delta y. So right below this, we have another example. This is find the volume of the solid generated by the region enclosed by f of x equals the square root of x, y equals 2, x equals 0, and revolved around the y-axis. Sketch the region, solid, and typical disk or washer. First thing that we need to do is sketch this. So I'm going to go ahead and sketch our square root of x. I also want to note that we are going to be rotating this around our y-axis, so keep that in mind as we draw this. So I'm going to make sure that I leave some space to the left of my y-axis. As I rotate it, it's going to go that way. So we are sketching a square root function, and I do note that I have x equals 0, which is the vertical line on the y-axis, and then we also have y equals 2. So we would go up to 2 on this. And then graphing that square root function, we have 0, 0. We have 1, 1. And then the square root of 4 is equal to 2. So I'm going to go ahead and shade our region that we have here. And this time, as we rotate it, we're rotating it around, like it says, the y-axis. And so as we rotate that, this shape is going to reflect. I'm just going to go ahead and sketch it roughly. And as we rotate this, I'm going to go ahead and draw a approximating rectangle. So as we rotate this, it's going to make that three-dimensional shape. It looks almost like a horn, but pointing upwards, or a flower. And that rectangle is going to get rotated around. And as it rotates around, it is going to make a circular shape. And so this is actually going to be an example of a disk. And so in order to find the area for our disk, it's pi r squared. And so pi r squared. So let's talk about what the radius would be. So the radius here, r, depends upon the function that we have that we just sketched, which is y is equal to the square root of x. Now I am going to, and also delta y, since we are rotating this, we have a thickness of delta y this time versus delta x, because that rectangle is horizontal versus vertical. So when I write my area, because of the delta y, I need to make sure that my function is in terms of y also. So this is going to be pi times, and then to rewrite this in terms of y, square both sides. I get x is equal to y squared. And so my radius is going to be y squared. So that radius would be y squared. And so to calculate our volume, we're going to have pi times the integral, and these are going to be the y values that we're integrating from. So it's going from 0 to 2. And then we have, so we had pi r squared. So our r squared is going to be that y squared, which works out to being y to the 4th. So y to the 4th, and then that thickness, which would be our dy, our delta y. And so integrating this, we still have a pi out in front, and then we have 1/5 y to the 5th, evaluated from y equals 0 to 2. So then substituting in our upper limit of integration, we have 2, minus 0 when we substitute in our lower limit of integration. Working this out, we get 2 to the 5th over 5 pi. So this works out to being 32 over 5 pi. So the next example that we have says, find the volume of a solid obtained by rotating the region bounded by the given curves. We have y equals 1/4 x squared, x equals 2, y equals 0, about the y-axis. Sketch the region, the solid, and a typical disk or washer. So the first thing that we're going to do is sketch this. Since we're rotating this around our y-axis, I'm going to make sure to leave some space as I draw this to reflect over there on that other side of my graph. So sketching this, we have the line x is equal to 2. And we have the line y is equal to 0. And from here, and then also remember that we are dealing with that positive region in here. So the next thing we have is going to be y equals 1/4 x squared. So if we were to square the largest value that we have, which is 2, 2 squared would be 4 times 1/4 would be 1. So the height of this, the highest that we're going to have is only going up to 1. And so 0 squared is 0. Substituting in 1, we get 1/4. And then substituting in 2, we get 1. And so you can see the region that we are dealing with, I'll go ahead and shade, is given. And then as we rotate this, that is going to go ahead and rotate around. And again, we're rotating this around our y-axis. So it's opening up here. And if we had a rectangle, since we're rotating around our y-axis, I'm going to go ahead and draw my rectangle here. And as we rotate it around, it's going to end up on that other side. But you'll notice that there's going to be an inside of this and an outside of the rectangle that we're rotating around. And so this right here is definitely a washer. So we are dealing with a washer this time. And so with washers, we have to talk about the inner and the outer radius. And so looking at our inner radius and our outer radius, the inner radius is determined by that function that we have, and our function was y equals 1/4 x squared. And then the outside radius is determined by that vertical line that we had, which was just at x equals 2, and that never changes. So that outer radius doesn't change. The outer radius is going to always stay at 2. And so now we need to look at the inner radius. And our inner radius changes based upon the graph that we have, which is 1/4 x squared. And so since we're dealing with a delta y here, since we're rotating this around that y-axis, I need to make sure that that function is written in terms of y, and right now it's in terms of x. So I can rewrite this as 4y equals x squared. And then taking a square root on both sides, I end up with x is equal to 2 square root y. Simplifying that, square root of 4 is 2. And so my inner radius is going to be defined by this function that we have. So our inner radius is going to be 2 times the square root of y. And so in order to find our area here, we are going to do pi times the outer radius squared, so times 2 squared, minus pi times our inner radius, which is 2 square root of y squared. And so in order to calculate our volume, I'm going to go ahead and factor out that pi and have just 4 minus, and this is going to simplify to 4y. So we're going to have the pi, I'll put out in front, the integral from, and since we're dealing with y values, we're just integrating from 0 to 1. And what we have to integrate is 4 minus 4y from down below. And then that thickness of that washer, which is going to be our dy. And then integrating this with respect to y, we have a pi, and then we have 4y minus 2y squared, evaluated from y equals 0 to 1. So substituting in 1, we have pi times 4 minus 2, and then substituting in 0, we just get 0. And then this works out to being 2 pi. So it also says down below, we can find the area of solids that are not solids of revolution. So the example right below this. And so we're going to go ahead and work on this example together in class.